Today, we're going to talk about something called the standard normal distribution, also known as the Z distribution. Now, we've already talked about normal distributions, right? They follow a bell curve. We talked about standard deviations, all that kind of stuff. But, statistics is often used to compare completely disparate sets of data. So how do we do it? Well, every normal X distribution, normal meaning, bell curve follows bell curve. That's what they mean by normal. Every normal X distribution can be transformed into the standard normal distribution using this transformation. And it is a transformation. You have to be able to use this formula. Not just, oh, it's in my reference sheet, so I don't need to understand it. No, you need to be able to use it and understand what it's doing. What the standard normal distribution does is it takes a distribution with any mean and standard deviation size of yada, 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 and it forces it to fit the same kind of curve. That's why we call it a transformation. It forces it to fit the curve. You get a z-score, which you've probably heard of. I'm hoping you've heard the term z-score before, but maybe you haven't. It's not a big deal. A z-score is literally the number of standard deviations you are away from mean on the standard normal distribution. So if I say a z-score of 2.3, that means 2.3 standard deviations above mean on the standard normal curve. That's what that means. So the transformation is x minus mu over sigma. So I give you, some set of data. I tell you the mean is 20 and the standard deviation is 1.5. And I go, what's the z-score of someone that gets a 21.7 or something like that? And you would go, okay, 21.7 minus 20 divided by 1.5, and it would spit out a z-score. The Z distribution has a mean of 0 and standard deviation of 1. You may not have realized this, but when we were using the graphing calculator before and we did the whole second vars, normal, CDF, did anybody realize that it defaulted to mean of 0 and standard deviation of 1? And then you had to change it? That's because that's the standard mean, the standard deviation. Crap, I didn't mean for it to sound like that. But it defaults to 0 and 1. Mean of 0, standard deviation of 1. So we say Z is distributed normally, 0, 1, mean of 0, and standard deviation of 1. So I've already said this, but the z-score is how many standard deviations X is from the mean. Z-scores are useful when you're comparing two populations that have different means and different standard deviations. That's what it's good for. The comparisons are only reasonable if both distributions are approximately normal. Okay. So here's a really good example. It says Kelly scored 73% in history. Before I even read this question, you ever go home and your parents like, how'd you do on the test? And you're like, oh, I got a 75%. And your parents are like, oh, and you go, but the class average was a 60. So then you're like, so even though my score wasn't great, I really did stand out against the rest of the class. Honestly, who cares? All we care about is how you did as parents. But the point is, we've all done it. We've all been there, right? Okay. So Kelly scored 73% in history, where the mean was 68%. The standard deviation was 10.2%. But in math, she scored a 66%. Oh man, that's bad. The class average was a 62% with a standard deviation of 6.8. So what we're really wondering is, which one is she better at compared to the rest of her classmates? In which subject did Kelly perform better compared with the rest of her class? Assume the scores for both subjects are normally distributed. Now you can't just look at this and say, she's better at math because she was closer to the average, or she's better at history because she, is 5 more than the average. You can't do that. So what we do is we convert both of these things to standard normal, and we get a z-score for both classes. And whichever one has the higher z-score, that's the one she's better at. It literally transforms. It forces both curves to fit the same shaped bell curve. And then you get z-scores. So for history, see, I didn't give a whole lot of space. You don't need much. Oh, and I have my graphing calculator open, ready to rock and roll. So make sure that you have yours ready to go. History and math, right? So for history, I'm going to develop my z-score. I want to know what her z-score is. So z equals, I'll actually write the formula, x minus mu over sigma. Our x for history was 73%. The mean was 68. And the standard deviation was 10.2. So you did this on a calculator, and you get a z-score of around, because mistakes, you get a z-score of around 0.49. That means in that class, her score is almost a half a standard deviation above mean. Almost a half standard deviation above mean. It's pretty good. In math, same formula. Whatever x score we're talking about, we're going to subtract mu, or divide by sigma. This one was a 66. Mean was a 62. Standard deviation was small though, nice and tight, 6.8. When you subtract and divide, you get 0.588. So even though she got a 66% on that math test, compared to the rest of her classmates, she's better than them. She's better at mathematics than at history, compared to the population. This kind of math is important to you. This is how IB tests or IB scores are developed. This is how AP tests are scored. So those either in AP classes, or you're all in an IB class right now, but AP classes, especially AP mathematics, I know that one for sure, you can never say like, oh, a 75% passes, that's going to get you a 4. No, we don't know. See, what they do is they collect all the scores in the nation, and then they use standard normal distribution to figure out where the standard deviation cutoffs are, and that's where they put their values of 1, 2, 3, 4, and 5. And IB basically does the same thing too. I mean, they play a little bit with it, a little more than that. They do something slightly more, what's the word I'm looking for? Not advanced, but complicated, I guess you could say. That's still not the word I was looking for, but they go over and above that, do some slightly higher statistics, but that's how they develop those scores. So what do we say? We say Kelly's results in math were better compared to her classmates because she is further above the mean. Kelly's results in math are better. Whoops. I have to write so slow because it's lagging so hard. Speaking of lag, there we go. Kelly's results in math are better compared to her classmates. Because she is further above mean. And there is absolutely no way you would have known that just by looking at the data that was given to you. We had to convert to z-scores to figure out which one is she better at compared to the rest. Interesting, huh? She scored lower, was closer to average, but that small standard deviation of 6.8 made a big difference. So these bottom ones, you're literally just using the calculator. And I'm going to use the calculator correct this time because I misspoke last time. I tried to correct myself in a remind, but very few people said anything about it. So it leads me to believe most of you just ignored the remind. When doing normal CDF, the calculator can go left, right, and center. I'm sorry, because it asks you about the lower bound and the upper bound. I was thinking about the thing that I'm going to teach you tomorrow. Tomorrow on the older calculators can only go left. But as far as normal CDFs are concerned, you can establish a lower bound, you can establish an upper bound, you can establish both. So for the first one, we are going to establish both an upper bound and lower bound. It says to illustrate, but that would just mean you just draw the bell curve. I'll do it one time. I'm not going to draw 3 different bell curves because you get the idea. So let's see, x-axis, bell curve, mean of 0 because it is the standard normal. Negative 0.41 is below, and positive 0.67 is above. And we're just trying to figure out how much area is covered, which means what's the probability something lands there. So let's go to the calculator. It's still normal CDF. So second vars, normal CDF. We're going between negative 0.41, so that'll be our lower bound, negative 0.41. And our upper bound is 0.67. And look, mean 0, standard deviation of 1. It defaulted to that, which is nice. So we don't have to change that because we are in the standard normal distribution. There you go. What's the probability something's going to fall between those two bounds? About 0.408. So if your calculator said error, you probably used a minus sign instead of a negative symbol.
That's true, I did.
About 0.408. So we say that the probability of that occurring, negative 0.41 less than or equal to z less than or equal to 0.67 is about 0.408. There it is. And we just do the other two on the calculator as well. So this part B, it has an upper bound, but it does not have a lower bound, less than or equal to 1.5. Go to the calculator. Second vars, normal CDF. The lower bound is, I wonder if the calculator will let me type 0. Let's find out. The upper bound is 1.5, and the rest of it stays the same. Let's see what happens. 0.433. I could. Why do I have 0.933 on my paper? That's definitely wrong. It's 0.433. What's that? No, I think I just misread the calculator. So this was part B. And then part C, this thing will be all over the place. Probability that Z is greater than 0.84. All right, now this one doesn't have an upper bound. This doesn't have an upper bound. Vars, normal, CDF. But it does have a lower bound of 0.84. So what do we do for the upper bound? I don't know. How about a big number?
200.
I don't know. I just typed a bunch of zeros.
Does it matter?
Just a bunch of zeros. Just give it a bunch of zeros.
My calculator messed up.
How is the calculator messed up?
Well, it says
0.2. That's 3 sig figs. Yeah. About 0.2 is 3 sig figs. There it is. That is the, no, it's 0.200.
oh, because it's a 4.
Yeah, but IB Math doesn't really care if you have the trailing zeros. Yes?
Why can't the upper bound be like any number, like any big number?
It just, because what you're telling it, when you tell it, what I type, like a million? I told it a million standard deviations above mean. I mean, realistically, after 4, there isn't going to be a difference. So as long as you type something with a bunch of zeros on it, you're good to go. Then the calculator defaults to 1 times 10 to the positive 99, which is outrageous. And it's not, you know what it's going to change? It's going to change the decimal, like 100 or 200th decimal value somewhere down the line. But you're only going to 3 sig figs anyway, so just type something like 1,000, 10,000, something like that, and you're good to go. Yes? Why would you do that? Because we don't have an upper bound. So we picked a number that is statistically impossible, so we know it's not going to change much for us at 3 sig figs. Yes?
With like the lower bound, when you put in 0, would you just do that every time
if you don't have a lower bound, you can't go below 0. You know, well, no. That's why. That answer's wrong. That's why. I typed in 0. That's stupid. The lower bound can't be 0. That's mean. Good gravy. Holy cow. That's why my answer on my paper is different. I went between mean and 1.5. No wonder. Okay. This is all kinds of wrong. Thank God Vivian asked the question.
But why? I can't even get the original.
Second vars, normal CDF. The lower bound needs to be negative like 10,000 or something. I just did, a whole bunch of zeros. And then the upper bound was 1.5. There we go. That's going to be appropriate. 0.933. There we go. Yeah, I went between mean and 1.5. Schmuck. Thank goodness Vivian asked a good question. I even questioned, I was like, why is my answer on my paper so different? Because I'm a ding dong. There we go.
Wait, how do you know how do you know when to use the different
I can't hear your questions over all the voices. I'm so sorry. What were you asking?
So I guess how do you know when to use a different number like that?
Oh, well, because it said less than 1.5. So I had to go all the way to the negative, ridiculous small stuff. So again, 4 standard deviations below mean is statistically impossible. I told it go 1,000,000 standard deviations below mean. That means you've covered it all. That's what I was doing.
So then it would be 1.5 upper.
Yeah, 1.5 is the upper because I was going to the left of that number. 0.933, yeah. Which is a much better value. Makes a lot more sense too.